more about the management methods, not so much about the tools of the um, statistical tools, but more about management methods. And as I told you before, one of the TQM methods is SPC. Of course, SPC is a statistical tool, and um, SPC means to to um, to let quality charts run in the production, and from time to time, one time a shift, two times a shift, you take samples out of the production, and then you measure the parts, and you put the values into the quality chart, control chart. And if one quality control chart is completed, if it has 125 values, at least, then you can calculate CP and CPK. CP and CPK are the process capability values, and CP and CPK can be calculated like I told you before. Last time I explained this sheet to you. I think this was the last sheet, like last time. CP is only about the distribution. Here we have the upper and lower specification limits. Here the 6 times the standard deviation. Here we have the CPK value, two equations. Here we have the upper specification limit in the equation, and here the lower specification limit. The smaller value is the correct value. And as you see here, you can estimate the standard deviation, sigma roof. There are 3 options to do this. At first, you can take this equation as which I showed you before in the first lecture, QM1. This is estimation of the standard deviation on the basis of the mean of the ranges. Here it is the mean of the standard deviations. And the third option is, and this is maybe the best option, you can take the upper confidence limit for sigma. I will show you how to calculate this next time in QM1. But this would be the best option if you take the lower confidence limit for sigma roof. It is the best case, and if you take the upper confidence limit here for the estimation of sigma roof, then it is worst case. We will need this in the homework. So this is a thing you can put the worst case in this equation, and then if you do this, it is a very good estimation of the CPK value. Okay. Okay. If you take the lowest value here for CPK, then it is the right one. So you have 2 CPK values here, and the lowest is the right one. Mostly the CPK and CP requirements in the industry is 1.33 or more. in the practical work in the industry, if you have a higher CPK and a higher CP value, the standard deviation would become lower. As you see it here, you have a CP and CPK of 1, here of 1.3, and here of 1.67. And the higher the CP and CPK is, the higher the process capability is, the lower is the standard deviation, the better is the precision of the manufacturing or of the production. There is a book you can get in bookshops. It is written about from the author is Kiki Bothe. Originally it was only in English available. World Class Quality was the name. In the meantime, it's also available in other languages. And here they have an analysis made in the 70s and in the 80s regarding supply companies in the automotive industry. And they have involved 14 or 15 supplier companies of the automotive industry here in the US and in the USA. In the 70s, these supplier companies had a quality level of a CP value of 0.67, which is pretty bad. And you have to separate, you do separating action to find out which parts and which products does not meet the top of the specification, which are outside of the tolerance. In the US in the 80s, they had a CP and a CPK of 1.2, which is also not so good. Japanese supplier in the automotive industry had 1.33 in the beginning of the 80s, and in the mid of the 80s they had 1.67. In the meantime, there are a lot of companies who are who have a requirement to their suppliers to have CPK and CP values of 2, which is the same thing as a Six Sigma quality. So this means the requirements on the quality in Sega's production has become higher and higher, and in many cases today the big companies like Motorola, General Electric, or Siemens, or whatever, they are requiring Six Sigma quality. And if there is a supplier who says it is not possible to do this, then he must find arguments and must discuss the reasons with the customer company why it is not possible. It is not enough to say only simply it's not possible to do this. Then the question is why? Why is it not possible? And in the next step, the customer company is sending some auditors, and they are going very deep in detail in the processes, and they find, and then they maybe it is not possible to get the CPK or CP of 2 or Six Sigma quality, but in many cases the supplier company must do some actions to go into to reach this goal and to come into this goal of a Six Sigma quality. Not in every case is possible, but this has to be proved in practice in audits. Now, these sheets, I took it here. I took it in the strip. Here you see the warning level limits and the specification, the control limits of control charts. This is here an example for mean charts without a tolerance regarding if the sample size is 3 or if the sample size is 5. Then you can calculate here the the upper warning limits and the upper control limits, lower warning limits and lower control limits. So this is for mean charts, for arithmetic mean. This is for range charts, the same. Also the limits, warning and control limits. And here we have it for the S charts, for the standard deviation charts. But this is not equal. This is another example, what you see here on the sheet. This is by the VDA. VDA is the German Automotive Association. And so every big company has special equations and special factors here for calculating control limits and warning limits. It's not all the same. Here's some special things. If you have, in many cases, you have a production 1 here, and this production has a mean value and a standard deviation. You can calculate the control limits for the control charts. Then you stop the production because you have produced enough products. Then the next order is coming, maybe after 1 or 2 months. And then you go into the process again. The process is running a few weeks. Then you stop the production again. And the second production has that mean value here. These control limits, as you see here, production 2 and the same production 3. Maybe they stop the production again for 1 or 2 months, and then they go again into the process and they are producing a third time here, several products, and this is the third production. Between every production, you see a difference of the mean. So this means the mean in every production is another mean than in the production before. And here, in this case, over the time they take, in many cases, they take the upper control limit over a longer period of time, maybe in a time of productions, 3, 4, 5, 10 productions, whatever, about productions over a half year. And then they take the biggest, the maximum control limit and the minimum control limit for the future. So this means there can be a jump, there can be a drift or a variation of the mean value from production to production. But if it is inside the specification limit, then mostly they're analyzing this over a period of several months, maybe 6 months, and then they say, okay, if the quality every time is in the specification limits, then we take the maximum control limit and the minimum control limit of the last 4 or 6 or whatever productions. That means for the future, then, for the total production, they take the upper specification limit of the production number 3 and the lower specification limit, the lower control limit here of the production number 2. UCL of 3, LCL of 2. Also, a special thing is quality characteristics which you cannot measure directly after the production. Just an example, this is an example by the shrinkage of a polypropylene plastic component. Polypropylene has a post-shrinkage. It is a shrinkage after cooling down. When it is at room temperature, then it starts the shrinkage process, and the shrinkage process means that the dimension would become smaller and smaller. And this lasts in this example until 140 hours. After 140 hours, these parts have their end dimensions. So this means it depends on the point of time when you measure the parts. If you are here in this area, it is not the same if you measure the parts after 1 hour or after 5 hours or after 10 hours, because every time you will get other values because of this shrinkage curve here. So there are some quality characteristics that are changing over time, and it takes some time until they reach their final values. So in these cases, you must make sure that you measure the parts always after the same time after production, not in one case directly after production, then next time one day after, or if there is a weekend between the productions after 2 days or 3 days. This is not so good, because then you are here in this curve on different parts of the curve. So if there are some quality characteristics who are changing over the time, then it makes sense to do a study, to do an analysis about this curve, how this curve would be. Well, this is an example here about the shrinkage of a polypropylene, a plastic component of a length dimension. What are further examples? There are other examples, of course. If you think of the cooling of metal, of steel parts, which have a big wall thickness, it can last several hours or maybe 2 days until they are cooled down to the room temperature. Also, if you think of painting, printing, gluing processes, it lasts some hours, maybe minimum some minutes, maximum some hours or days, until the solvent is disappeared completely. So you cannot do any tests of the painting or the printing or the gluing after the quality characteristic has reached its end, its final value. There are other examples. You have burn-in processes. If you think of electronic parts, PCBs, printed circuit boards, in the electronic field, you have a burn-in process, and you can test these PCB boards only after the burn-in, not before the burn-in. So maybe the burn-in lasts 1 day or 24 hours, don't know, depends on the product. Then you cannot test it before. You have to test the values for the control charts or whatever for the quality assurance. You have to do the tests after the burn-in process. Also mechanical parts. If you think of motors for cars, the cylinders of automotive motors, they also have a burn-in process, which lasts several hours. And only after this time, after this burn-in process, you can take measurements on the product. So this is a thing you have to have a look at it. Which quality characteristics can be measured directly after the production, and which quality characteristics change over the time, and when do they reach their final values? SPC is one of the TQM methods, as I told you before last time, there is always a time delay between the part production and the measurement. And this is one problem with SPC. Another problem is the high measurement effort. If you have many quality characteristics or if you have many cavities, then the measurement effort can be high. Also, you have one disadvantage: you have no quality data, no measurements between the samples. So if you take a sample out of the production one time a shift, then there are several hours you're without any information about the quality. So the interval between taking the samples, it is there's no rule about this. You can every company does it with the experience. They don't. There is not a formula or an equation. It has to be defined on the basis of experience. And if you take samples out of the production, you don't have any information about the quality between the sample, between the samples. Also, in SPC, in many processes in the industry, a closed loop process is not possible because they don't know which factors are influencing the quality characteristics in which way. So these relations between the parameters, machine or process parameters, and the part quality, the quality characteristics, not in every case are known. So it is not so easy to do corrective actions on the process if a control chart is running out of the control limits. SPC is only a monitoring system, but it is not an optimizing system. And then this also is a special case here, a single site limited quality characteristics. Just some examples: the ovality, if the part is not round, exactly round, it cannot be lower than 0 because then it is round. Also, another example: the roughness. The roughness can never be lower than 0 because then it's smooth. And the unevenness, the flatness of a part can also not be lower than 0 because then it's flat. So there are some quality characteristics that have a natural limit. They cannot be lower than 0. And then you don't have a normal distribution, as we saw this before in QM1. You have a kind of normal distribution, but it is limited by this value in this case here by the 0. And then in practice, it is only a part of the bell curve here. You have a mu value. This is the value with the highest frequency. So most of the parts have this value. This is mu. And bigger than mu, larger than mu are all these parts here. And lower than mu are all these parts, but no part can be lower than 0. So in these cases, when you calculation of CP and CPK, you can only take one of the equations, the equation where the upper specification limit is integrated, because the lower specification limit makes no sense. So you take the upper specification limit, like you see here, this blue line, and only this equation for CP and CPK is valid, is to take. So there is only this upper specification limit is to be used, and there is only CPK value to be taken for the quality charts and for the process capability, because the CP value doesn't make sense. The only thing is, maybe this is an option to take the CP on half of the distribution, maybe here from the mu to the upper specification limit. This is maybe an option. You can perform this, but in most of the cases they only take the CPK, one formula with the upper specification limit. Okay, so much about statistical process control, SPC. Another TQM method, which is a very powerful tool for process analysis and optimization, is DOE, design of experiments. And the design of experiments are a lot of different, this is a toolbox, and there are a lot of different methods, DOE methods, which can be used. And what I will show you here on the next sheets is the most popular and the most popular way to use DOE methods. Well, at first you have to know that there are, for process optimization, there are offline methods and online methods. The DOE methods belong to the offline methods. DOE, design of experiment, this is the traditional DOE, but also Taguchi methods, DOE methods, Shinin methods, all developed and invented in Japan, and also robust design. This belongs also to the DOE. And all the DOE methods are offline. This means these methods are performed before the series production is starting. So we have a series production of 100,000 parts a year or 500,000, and it is the goal to take DOE methods before starting the process to find optimum process conditions. This is the goal. So this is a part of the development process in the beginning and the planning of the production. It's before the production starts. Online methods like the gradient method or evolutionary operation methods, neural networks or multiple regression models, these are methods. These methods here are used in the production, and you can only do variations in very small steps because you don't want to generate parts that are out of the specification. So you want to sell all the parts. This means you can only do very small variations and very small optimizations around the process point. The machine setting can be changed only in a very small way to avoid scrap and to avoid parts that you cannot sell afterwards. So these online methods are methods used in the production, and the offline methods are before the production. DOE is a method to use before the production. In the production process, you are making analysis by SPC, as we talked before, but SPC is only documentation. You take samples out of the production and you get information about the quality, and if the quality is okay, then everything is fine. But if the quality is not okay, then you have to do corrections in the process. It is a kind of preventive method because it is before scrap is generated. So the idea is to have a look at the process directly in the process to avoid the production of parts that are out of tolerance and you cannot sell these parts. So in this case, it is a preventive method, but on the other side, it's in the production. So it is very at a late point of time not in the quality planning, in the development phase, it's in the production phase. And this is more late, not so early. The goal of all these quality methods are to get a process under statistical control. This means today you have this distribution, tomorrow you have this distribution, and next day you have that distribution, every time another mean and another standard deviation. So you have to bring the process under control, because this process here is not under statistical control. There are systematic factors which disturb the process. If the process is under control, under statistical control, maybe the variation is too big. Then the goal is to reduce the variation, to make the variation smaller. This is the goal that you have in every quality method. First goal, to do a centering of the process, to bring the mean to the target, and then to get a low variation, to get a high manufacturing precision. These are the goals. What are preventive concepts, approaches to reduce systematic variation? How to use this systematic variation? You can maybe, these are only examples here, classifying and standardization of production equipment, production conditions, systematic standardized start of the production process, preventive maintenance procedures, systematic incoming inspection for the purchased parts or for the material, special equipment to avoid exchanged assembly, window nets for insect protection, SPC, DOE, or training in quality methods. All these things are preventive concepts to reduce systematic variation. Now, this is an example how to use DOE methods. And DOE methods are used at first in the beginning of the process before starting the series production. Maybe you have a prototype tool, but this prototype tool, this test tool or test process, has to be similar or nearly the same as the later production process. If you think of injection molding of plastic components, you need a steel mold, and most of the geometry of the inserts here has to be as later on in the series production. Also, it has to be a steel mold. So everything has to be very close, very near to the later production. Then you do experimental design. The heart of the main thing of the DOE is a parameter design. This means you have an experimental plan and maybe a 2-high-3 plan or whatever, and then you are doing a variation of quality of parameters or factors which influence the quality, like melt temperature, mold temperature, holding pressure, and so on. And then you have some other parameters you can also integrate in experimental plans or experimental designs. Then you have the series mold, and you try the best machine setting you get out of this DOE optimization, and then you can check if the tolerances are okay, if you can meet the requirements, if it is a robust process, and you can also check if the process capability is high enough. Taguchi was one of the inventors, one of the first engineers in Japan. He was in Toyota, and at first he was in Toyota, later on at Ford in the US. And he has invented the Taguchi method, which uses a lot of DOE methods. The Taguchi methods has 3 steps. First step is system design, then parameter design. The second step, the third step is tolerance design. What does this mean? System design means you have to define the machine, the material, all the process things. You have to define the process which has to be optimized. This is a thing you have to do in the beginning of every DOE analysis or optimization system design. So the definition of process, of the machine, of the tests, of the test equipment, and of the material. The second step is the parameter design, and the parameter design is the experimental design. So you have several parameters on the process, and you are doing a variation with these parameters, and then you are measuring the effects of these variations of the parameters. So this is the experimental design and the analysis of these experiments, DOE experiments. And then on this base, you have to check if the tolerance is okay, or if you have to take maybe other material or other machines or whatever. This is the final step. So these are the 3 steps, and the main step, of course, is the parameter design here in the middle. Taguchi was the first one who said that it is not so correct what designers are doing here in most of the companies in Europe or in Japan or in wherever, US, wherever you look. The designers say, okay, there is an upper specification limit and a lower specification limit. And if the quality is between the specification limits, then the quality is okay. If it's outside, there is no quality, there is crap, and you cannot sell the parts. So inside is okay, outside it's not okay. This is a black and white method. So inside there is no loss, you can sell all the parts, and outside there's no quality, you have loss. Taguchi was the first one who said this is not so true. It is more like a curve. The curve like you see here. This curve means that the loss is only a minimum in the area of the target value. There's a small area here around the target where the loss is very low. And then the loss is increasing even inside the tolerances before the quality reached the upper specification limit or the lower specification limit. Of course, the loss is very high outside specification limits, but the new idea or the new approach was that he said, okay, even inside the tolerance area, you have loss. Why is that? Because this is what he can show. He could show that the probability that a product fails and becomes defective is the earlier the more the distance is from the target, even in the tolerance area here. So the probability that that a TV set is going defect after 5 years and not after 10 or 15 years, the probability is the higher the distance is away from the target here. And it's also, he had shown this and proved this in many cases, in many examples. Maybe a component in a car is maybe it is getting cracks, or it is making noise after 2 years or 3 years and not after 15 years. The more away the value is from the target. So even inside the tolerance, this is what he found out. And now the next step is if you do a combination of this loss function here with a normal distribution, then the area below these two curves here, this integral, this is the loss. And now, if it is possible then to get a small variation with a small distribution with a low variation, then the area below these two curves are minimized. But this is only possible if the process is centered, if the process is exactly on target, if the mean value here is on target. If the process is not centered, like you see here, then the area below the two curves is getting bigger. So there is more loss. This area here, this gray area, this is the loss. Again, two requirements: centering of the process is the first requirement of Taguchi, and the second requirement, of course, is a low variation, small standard deviation. The Shinin method is similar to the Taguchi method. Shinin also was a Japanese engineer, and he was also in Toyota at the beginning, and he is the founder, inventor of this Shinin method. He used only factorial experimental designs, full factorial experimental designs. This is much better than the Taguchi designs. In many cases, the Taguchi designs have some problems, so it is not so good to use Taguchi designs. It is better to use full factorial experimental designs. It has to do with confounding, but this is very special and it would go too much in detail. but generally spoken, a full factorial experimental design is much more safe than using a Taguchi experimental design. Anyway, next step is variation plots, or he's calling this, Shainin called it scatter plots. Then you have the verification, a verification run, to analyze if it is better after the optimization in comparison to before the optimization. Here's some examples. This is an example of the roughness of a ceiling area of a pump housing. And you see the roughness here depends on, in this case, on the molding of the housing. The molding, it is an industrial molded plastic component. And here there are some machine settings. Here you see a machine setting with a very low roughness and small variation. And here you see a machine setting with a high roughness and a bigger deviation, standard deviation. So this means there are some process settings of the machine which are better for quality, for low variation than other process settings. In this case, the ceiling, the company who was supplying the rubber ceilings here, they say you need an RA value of maximum 1 micron. It must be lower than 1 micron. And here you see only this machine setting can meet the requirement. This machine setting here is not able to meet the requirement. Here you have a mean value of about 2 and a high standard deviation. So it's possible, and this is shown by this example, it's possible to optimize variation and also the mean to get a low roughness here by using DOE methods. Yeah, this is only a picture of the pump housing, and this was the ceiling area here. You see this, and he said it has to be a very low roughness of about 1 micron or low. And here you see the means of several experimental runs. They test experiment 1, 2, 3, 4, and so on. There were 8 experiments. It was a 2, high, 3 plan. 3 factors are changed in the setting, and then they have 2 levels of setting, a low level and a high level in the setting. And these are the effects. These are the results of the 8 experimental runs. And you see the roughness is very low at 2 experimental runs, but the other experimental runs have much higher roughness. And here, in addition, they had made additional test runs, but these test runs has also a result of very high roughness. So the best roughness here is experimental run 1 and 2. All the other things are the same, are constant. Material was constant, so the plastic material constant, the machine constant, the mold, everything. Only the machine setting, they had changed the machine setting. It's also possible to make an industrial process more robust than at another machine setting. This is shown here. Here you see again, this is a dimension here of a plastic component, and this is the timeline here, 5 hours, 10 hours, 20 hours. And you see after 10 hours, the old material batch was changed because they don't have any more material. The material was over, then they need other material, new material batch. And this new batch caused a jump of the mean value and also an increasing of the standard deviation. This is for the poor roughness, and if the roughness is optimized, they had also jump of the mean here, difference in of the mean value after the batch change. But this difference between the old mean and the new mean is not so high. It's very low jump. It's inside the tolerance area. And you can see it here, the length dimension, width dimension on the weight. So in the right line here, you see these, in these diagrams, you see the process has a better robustness against outer disturbances, and batch change of the material is an outer disturbance. So this is possible. You can do it with DOE methods. What do you need? Well, if you want to do experimental design or application of DOE methods, then you have to do a separation in machine parameters and process characteristics. The difference is machine parameters can be changed independently from each other. Here, this example is related to the injection molding process. And in this example here, every parameter here can be changed without influencing another parameter. So it is possible on the machine to change the mold temperature, and independently from this, you can change the rotation speed, the back pressure, the switchover point, the holding pressure, the cooling time. All these things you can directly set on the machine, and it is not influencing each other. So these parameters here must be integrated. Some of the parameters here must be integrated into the experimental design of a DOE plan, because you can it is only possible to integrate in a DOE plan those parameters who can be changed independently from each other. These characteristics you see here, these process characteristics, these characteristics cannot be changed without changing another one. So they depend on each other. And these parameters here cannot be integrated in an experimental design, in an experimental plan. Only these here in the yellow box can be integrated. Here in the orange box, it is not possible. These parameters you can use for the monitoring later in the production documentation of production control. Here you can use these process characteristics, but not in DOE. Both the machine parameters and the process characteristics have an influence on the quality characteristics of the part. And these are the things you have to measure, and these are the things which are interesting for the customer. Dimensions, weight, strength, roughness, and other things directly measured on the product. These are the product quality characteristics here. So again, in the experimental plan, in the experimental design, you can only integrate these parameters which can be changed independently from each other. Taguchi was one of the first who found out that if you are performing an experimental design, the result can be, in many cases, that you find out which parameters are control parameters and which parameters are signal parameters. Control parameters you can use to minimize the standard deviation, the variation of the process. So they are influencing the CP value in SPC. The signal parameters are changing mostly the centering of the process. And this means they influence CPK. So in many processes, you can find out after analyzing the experimental designs, the design of a DOE, you can find out which parameter, which machine parameter is more for the variation and which one is more for the centering of the process. The most important thing when using DOE methods is the effect analysis. What is an effect? An effect is the influence of a parameter on a quality characteristic. So let's say you have a quality characteristic, maybe a dimension, and one parameter is temperature and a second parameter is pressure. You can set the parameter 1, the temperature, at a high temperature, which is plus, and a low temperature, which is minus. So let's say, you can say the temperature is, don't know, 200 degrees is minus and 250 degrees is plus. You can define this completely free. So there's no limit what is minus and what is plus. So you can do a definition and you can say, okay, minus is 200 degrees Celsius and plus is 240 degrees Celsius. And if parameter 2 is a pressure, you can say, okay, minus is 100 bar and plus is 1200 bar. So you have 4 experimental runs. Here you see a minus for parameter 1 and 2. Here you have a minus for parameter 2 and plus for parameter 1. Here both parameters are plus, and here the parameter 2 is on plus and the parameter 1 is on minus. So you have these 4 experimental runs, and this is the smallest DOE plan that is possible. It is a 2-high-2 plan. 2 parameters are changed on 2 levels, a minus and a plus level. Now you produce 10 products on every of these 4 machine settings. So you have these 4 experimental runs, and on every experimental run, you produce 10 parts. So you have 10 measurements, and then you get a mean value. This is the mean of this experimental run. This point here is the mean of that experimental run. Here you have the mean of that experimental run, and here the 4th mean. So you have 4th means for the 4 experimental runs. And now the effect is, if you have a light shining here from the right side, the shadow here on this screen show the shadow of that point, the shadow of that point, and here on this side also the shadow of this point and this point. And if you take the mean of the shadow points and draw a line between these means, this is called the effect. And this is called the effect of parameter 2. And if you do the same shadow picture here on the screen in this dimension, then you have here the effect of the parameter 1. So this is the most simple plan because it is the smallest plan. But this method of finding out of analyzing the effects is every time is the same, even if the experimental designs are bigger. If you have a too high 3 plan or too high 5 plan or whatever, but you cannot show this in a 3-dimensional figure. So the best to show it is here in this simple 2x2 plan. If you have only a minus level and a plus level, you have a linearity between minus and plus, and you don't have any information if the linearity is okay or not. Probably it's okay, probably maybe it is not okay. So to get an estimation, if the linearity is real or not, you do one experiment in the middle, and this is called the central point Z, and this is one experiment directly in the middle. If you see this here, it is one experiment taken here directly in the middle of the variation area. This is the variation area here, and exactly in the middle. You do one experiment, also with 10 parts. Then you take the mean of these 10 measurements, and then you get an additional mean value. And if the mean value here is in the area of the line, then you can say, okay, it is a linearity between plus and minus. If the central point result is far away from the line, then maybe there is a non-linearity in the inner area here, and then you have to do additional experiments in the inner area. But mostly the center point, the result of the center point mostly is in the area here of the line. So in many cases the linearity is working. In DOE, it's also possible to find out and to quantify interactions. What is an interaction? Interaction is if the effect of a factor depends on the setting of another factor. Let's take this example. Here you have the holding pressure, this is one parameter, and here you have a dimension. Now you change the holding pressure from minus to plus, let's say from 200 to 1000 bar. Then if the holding pressure is higher, then you get a bigger dimension. This effect here is with a high mold temperature and also with a low mold temperature. Maybe a high temperature of 100 degrees Celsius and a low mold temperature of 20 degrees Celsius. These lines here, these effect lines, are parallel. This means there is additivity of holding pressure and mold temperature. Interaction is if the effect is different. The effect of the holding pressure is dependent on the setting of the mode temperature. In one case, here the mode temperature is on minus, and the holding pressure has no significant influence, no effect on the dimension. But if the mode temperature is on plus, the holding pressure has a much higher effect, a much higher influence. And this is an interaction. And you can quantify the interactions if you use DOE methods. Yeah, this is an extreme situation here. Here you have an increasing effect of the holding pressure if the mode temperature is high, and a decreasing effect of the holding pressure if the mode temperature is low. This is not so often here. Mostly interactions look like this, like you see here on this figure in the middle. Here you see the typical experimental design. This is a 2-high-3 design, a full factorial experimental design. And this design is used mostly in the industry. 2-high-3 is 8. And here you see 8 experimental runs. And here you have the factors, the parameters. Parameter A may be a temperature. Parameter B may be a pressure. Parameter C may be another temperature or whatever. Special process time or whatever. Here you see in this column here, in this column, the vertical line, you see 4 times plus and 4 times minus. So there are exactly the same number of plus as the number of minus 4. Here also you have plus plus minus minus plus plus minus minus, also 4 plus 4 minus, and here plus minus and so on, but also 4 plus 4 minus. So they call this design orthogonal. Orthogonal means exactly the same plus number of plus as number of minus. This is the experimental plan, and this is experimental run. The first experimental run, the second experimental run, the third until the 8th. At the first, all the parameters are on the plus setting. Here, all the parameters are on the minus setting, and in all the other combinations here are all possible combinations between the first and the 8th experimental run. Well, this is experiment number 1, 2, 3, and they are doing these. They are setting the machine on these experimental conditions here, all on plus. Here, these 2 on plus, the C, factor C on minus. Here, A and C are on plus, and B is on minus. So they are performing every experimental run and producing some parts, let's say 10 parts in every experimental run. So they have here 10 parts, here 10 parts, and so on. In total, they have 80 parts. And then they're doing the measurements of one quality characteristic or several quality characteristics. Here you see A and B and C, and also the interactions. The interactions can be calculated. They cannot be set on the machine. And the plus minus here is calculated. Plus times plus is plus, plus times minus is minus, minus times plus is minus, and minus times minus is plus. So this plus and minus column here is calculated. This is the interaction AB. This is AC. BC is another interaction, and ABC is the highest degree of interaction in a 2-high-3 experimental design. So what you have here are the main factors, the parameters ABC. Then you have the 2-degree interactions, AB, AC, BC, and you have one 3-degree interaction. This means these things are important, and the 2-degree interactions are important. The higher the degree of interaction, the higher the probability that this interaction is not important. So a 3-degree interaction, there is a high probability that this interaction is not so important, not so significant. But the 2-degree interactions, they are, in many cases, they are significant. They can be significant. The best is to do a variation of, to take for the variations in a DOE, you take the 2-high-3 experimental design. Taguchi proposed to take more than 3 factors in a 2-high-3 plan. He said, okay, the 3-degree interaction may be not so significant, maybe unimportant. And then he is putting a fourth parameter D on this column here of the interaction. So he is, this means that a generator is, a so-called generator is generated here, and the generator consists of all these, they integrate all the elements here, A, B, C, and D. This is the generator. And if you take this generator and compare it with the headline here, then the double elements are falling out. This means they disappear. This means if you take this generator on A, then A is double, because A is here and A is here in the headline. A is double. So A disappears, and what is remaining is BCD. This means A is confounded with BCD. If you take this generator and you combine it with B, then B is double. There are 2 B. And so remaining is ACD. So this means B is confounded with ACD. So these are the confoundings here. And you see that the main factors are confounded with a 3-degree interaction. This is not a big problem. But if you look at here, if you do a combination of the generator with AB, with this element of the headline, then remaining, it is CD is remaining. This means AB is confounded with CD, AC is confounded with BD, and BC is confounded with AD. So these 2-degree interactions are confounded with each other, and this could be a problem if there is a significant 2-degree interaction in the process. You cannot say in the results, you cannot say if the results, the effects are coming from AB or from CD, or if they're coming from AC or from the interaction BD or from BC or AD. So you have mixed effects, and this is the big problem with the Taguchi experimental designs. So one advice is to take the complete full factorial design. Now, this sheet is about the effect calculation. You can calculate the effect of A if you take the results of the experimental runs where A is on plus, and then you calculate minus the experimental runs where A is on minus. Here you have a quality characteristic, like let's say a dimension, and the mean of the 10 parts of the first run is 2, the mean of the 10 parts of the second run is 8, the mean of the 10 parts of the third one is 1, and here for the fourth experiment is 4. This is measured. These are the measurements and the means of the 10 parts of the quality characteristic 1, and here of the quality characteristic 2. Maybe this is a dimension, maybe this is a roughness, but whatever. Now, if you want to calculate the effects of A, you take these results where A is on plus, this is 2 and 8, and then you take the mean of this, so you divide it by 2, minus these experiments where A is on minus, this means 1 and 4. Also the mean of this, and then you have plus 2.5, this is the effect of A. Exactly the same you do with the effect, with the calculation of the effect of B. You take experiment 1 and 3, because at 1 and 3, B is on plus, and then you take experimental run 2 and 4, because B is on minus, and then you do the same calculation. The result is minus 4.5, and then you can do it also with AB. AB is on plus here, experimental run 1 and 4, and it is on minus on experimental run 2 and 3. And it's the same. You can quantify the interaction here. The result is minus 1.5. And then you can do it the same with another quality characteristic. Yes, here this is shown for the second quality characteristic. It's absolutely the same calculation here. Again, I showed you this calculation on the most simplest plan here on the full factorial design 2i2, but it is exactly the same thing, the same procedure if you are calculating the effects on a 2i3 or 2i4 or 2i5 experimental design. It's the same. As I told you, you can produce 10 parts at every experimental run in DOE optimizations. Now, these 10 parts per experimental run have one result, and this is the mean of the 10 measurements regarding a quality characteristic. But you have another information. You have the standard deviation. And if you take these two, the mean and the standard deviation, you can calculate the signal to noise ratio. And for every experimental run, you get a signal to noise ratio. This means for experimental run 1, you get a signal to noise ratio, also for experimental run 2, 3, and so on, until 8 if you have a 2i3 experimental design. So you can do the effect calculation not only with the means of every experimental run, but also with the S2N ratio, the signal to noise ratio. And this signal to noise ratio is a value for the robustness. So the signal to noise ratio is for optimization of the robustness, and you can see in the results, you can see in the analysis, you can see which parameters are important for the robustness and which parameters are not so important for the robustness. Now, if an experimental run has a signal to noise ratio larger than 70 dB, then this is very good. 60 to 70 dB, it's good. 50 to 60, it's mean, and below 50, this is not so good. It's a more poor robustness. And if the signal to noise ratio is smaller than 40 dB, this would mean that the deviations, the variations are much too high. So with the signal to noise ratio, you have a tool to optimize, to analyze and to optimize the robustness of a process. On this sheet here, you see the general method for DOE analysis. At first, you have to define material, machine mold, methods, measurement equipment, and the quality characteristics. This is called system design in the Taguchi method. Then you have to do the selection of DOE factors, maybe the machine parameters. And the art is to find out only 3 or 4 parameters. There are a lot of parameters, of course, but you need some experience to find out what are the most important factors, the most important parameters on the quality. And these are the parameters to be taken into the experimental design. The next step is the definition. What is plus and what is minus? So the minimum and maximum, which has to be plus and minus in the experimental design. Then you go on the process. Also, this means here you do the experimental design directly in the process, and then you're doing the measurements and the analysis, and then you check, you test what are significant parameters and interactions. You define the optimized machine setting, and then you make a verification run. This means you test the new machine setting, the optimized machine setting, against the older machine setting or the machine setting before, or whatever, or a poor machine setting. And then you can see what is the potential of the optimization regarding that process. Well, there is a lot of software on the market to do these optimizations. This is only an example here. Here you see these 4 machine settings here at the edges of this space, of this area. And what you see here is the response surface of this DOE. So there are a lot of software products on the market for DOE analysis. Yeah, this is also example. Problem here, this is the filter housing, and the problem here, you see all these cracks inside the part. So this is, the customer said that we cannot accept this quality, and they send thousands of parts back to the supplier. The supplier must optimize the process that the next parts in the future do not have these cracks inside the material. And with this, you can optimize with these methods. You can optimize the process. You can also optimize the variation of dimensions, optimize the reflection, the bending of a part, or the inner flash, or the part weight. So there are several possibilities and several potentials to optimize the quality of a part or of a product with DOE methods. Okay, then I would say we do the break here, and we will continue then on next Wednesday. Okay, are there any questions from your side so far?